Welcome back. Last we left, we talked about a lemma that we're going to use to sort of build some of these proofs, Theorem 3.4 and Theorem 3.5. Let's go ahead. This proof is going to be a little bit weird, and it's mostly going to be words, and we're going to sort of, you could maybe verify that it's true if you wanted to, I guess. It might be a fun exercise. So an elementary matrix E, okay, so what I'm going to say is write multiplication by an elementary matrix actually does the corresponding oh geez, I'm running out of space. Okay, fine. Column operation. So what's neat is what we're saying here is that okay, if I have an elementary matrix that maybe swaps row J with K, right? When I left multiply, it takes row J of matrix A and swaps it. If I right multiply, this elementary matrix is going to swap columns J and K on A. And that sort of makes sense because we have this rows by columns multiplication rule. And over here, right, the rows of E are going to get multiplied by the columns of A and do their work. Over here, the rows of A are going to get multiplied by the columns of E. And so instead of switching rows of A, it'll switch columns of A. We could do the same thing for the elimination one and for the elimination elementary matrix and for the scalar multiple elementary matrix. Then if we know the determinants of our elementary matrices, we can verify. And what you find out is if you want to find the determinants of these elementary matrices, the determinants of these E's, my elementary matrices, are exactly the sort of cost we pay for column operations. And so what that's telling me is that okay, remember we said if I switch, so I'm going to say the determinant of if I switch row J with K, when we do that with columns, we change the sign of the determinant. And you can go and verify that this exchange matrix that swaps J and K, it has a determinant of -1. If you do if you take the elementary matrix that takes row A and multiplies it, or row K and multiplies it by a constant A, you'll find that the determinant of that is that constant. It's A. And so if you do a column operation here, that's the cost that we pay. We had to keep track of those A's and it would sort of filter out. And then we also had the sort of elimination one where you would take a scalar multiple and whatever else. And it turns out the determinant of that is 1. And remember, we said that doesn't affect the determinant. So this is really neat. So what that tells me is that if I do some column operations on A, then this thing over here is this lemma is telling me that thing where we keep track of all of the column operations we do and have to sort of pull that out. That's exactly what lemma 3.6 is telling me. This is actually super neat because this stands as a rigorous proof and not just hey, guess what, it works. It's pretty neat. So we kind of have all of the pieces into play, and well, sort of what we're going to do is we're going to play out some ramifications of this with a couple more a couple more theorems. Let's see. Okay, so now I've got like a corollary, and I'm going to call it 3. I think we're at 3.7. Sure, why not? And this is going to sort of immediately follow from the lemma that we just proved, and it's pretty interesting because what we can say now is that like for any matrix A, and a sequence of elementary matrices, so I gotta be careful of the record button that I accidentally pushed 10 freaking times when I do this thing. Sorry. And a sequence of elementary matrices. Oops, I don't need to write the word of twice. So we like have a bunch, and like, I don't know, we've got like EI, and we've got like I goes from 1 to, say we have n of them, right? So we're going to do like n column operations on this thing. This sort of then should not be a surprise, but like that A, E1, En, the sort of determinant of all of these things, well, it's just the determinant of A times the determinant of E1 times the determinant of like E2, and then all the way out to the determinant of En, which is really nice. This is sort of like the lemma that we had earlier. This is just it sort of like played out n times in a row. And this is sort of an important piece that we're going to use to prove some of the theorems that we talked about before. Okay, so that's going to bring us to a lemma that we're going to leverage here to get some important results, and this lemma will be 3.8. And the lemma is like any invertible matrix is the product of elementary matrices. This is pretty big. I think we may have even said this before and proved it, but we actually have like a neat way of proving it now that we'll use. Okay, so what we know is that like, well, any invertible matrix, is row equivalent, right? That's what we said, to identity, right? So like we could do some number of row operations on an invertible matrix and we could get to the identity matrix. That's sort of like what we did. And so what I could write is that like, well, here's A, and I would do like one row operation and then a bunch of, maybe I need n row operations, and that gets me to the identity matrix. So that's something that we know, right? Okay. And then, well, if I wanted to get A back out of this thing, I would need to start undoing these operations. So maybe like the first thing I would do is I would undo the En on inverse, and then this would be, well, then I would have like En minus 1 all the way down to E2, E1, and then A, right? Okay, and then I could undo the n minus 1 step and the n minus 2 step and the n minus 3 step, and we know all of these elementary matrices are invertible, right? We actually did like a homework assignment on that, and what's more important is that the inverse of all of these elementary matrices are elementary matrices themselves. If you want to swap some rows, well, you just swap them back to inverted. So what I could do if I did this process like a bunch of times to undo all of the steps, I would have identity, and then I would have the inverse of the nth step and the inverse of the n minus 1th step. Oops, inverse there. and then it would all the way come down. I'd have the second step inversed, and then the first step inverse. And now look what I have. I have A written as the identity matrix times a series, and all of these are elementary matrices. So if I'm just going to switch the order here, and the identity matrix doesn't do anything because it just doesn't change anything when you multiply it. So I have A as like E1 inverse times all the way out times like En inverse, and all of these are elementary matrices. So here I wrote an invertible matrix, and it's the product of some elementary matrices. Any invertible matrix you can do that for. That's pretty neat. I think maybe we showed that before, but I don't know. We'll do it again just for whatever. Okay, so now what we're going to do is we're going to prove theorem 3.4, which was sort of what we opened this section with, and we said like I'm going to rewrite it right now. So theorem 3.4, and basically what we said was the determinant of A, I don't know why that T went capital, but the determinant of A is equal to the determinant of A transpose. So taking a transpose doesn't change the determinant, and we're going to actually prove that down here. Now that we sort of have all the pieces in place with our lemmas and corollaries and whatnot. So let's take a look. One more thing that I want to note before we really get into it, that for an elementary matrix, which is going to be sort of the building block here, so for an elementary matrix, like the determinant of that elementary matrix is the determinant of the elementary matrix transposed. You could check it. It's not necessarily that hard, but time is short and we're not going to do it. Also note that if A is not invertible, AT is also not invertible, and the theorem reduces to 0 equals 0, right? Because the determinant of a matrix, if a matrix is not invertible, it has a 0 determinant, and so the determinant of A turns into 0. If a matrix is not invertible, its transpose is also not invertible, so this one is not an invertible matrix, and it's 0. So we only need to prove or to show for invertible matrices. That's the good news. Okay. Well, then let's do it. Okay, so by lemma 3.8, A, the matrix that we're trying to show has the same determinant as its transpose, can be represented as the product of elementary matrices. So I can write like A is like E1 times E2 times En. And like I know that above we had like their inverses, but for simplicity's sake, we're just going to say that, you know, the row operations are what they are. Okay? Well, that means, right? Okay, well, check this out though, because corollary 3.7 says the determinant of A det A is really the determinant of is the product of the determinants of the elementary matrices, right? E1 det sort of E2 dot 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 det En. Okay, right? And well, okay, now here's the last part. Then that would mean det A transpose, right, equals, let's see, pause. I don't want to take the transpose. Okay, let's try this then. Okay, so A transpose is equal to like E1 times E2 times En transpose. And this is like a throwback. But remember that, like, okay, if I want to take the transpose of a product of matrices, I can take the transpose individually, but we also switch the order. So then this thing becomes En transpose times En minus 1 transpose times times E1. I can distribute that transpose through A transpose, okay? But then if I wanted to check the determinant of A transpose, I can take the determinant of this thing, En transpose times E1 transpose. But wait, because these are elementary matrices, so this just becomes the determinant of like En transpose times the determinant of like En minus 1 transpose times all the way down to the determinant of like E1 transpose. But remember, for an elementary matrix, we said that, if I can get my pen thing to show up here, the determinant of E is the same thing as the determinant of E transpose. So if I go back down here, this is really then the determinant of like En times all of these other things times the determinant of like E. And these are all just numbers, and if you take numbers and you multiply it like in this order and you multiply it in this order, you're going to get the same thing. And so we then can conclude that the determinant of a matrix A is equal to the determinant of its transpose. That is pretty neat. That's a neat proof. We're going to take a quick pause, and then we'll come back and prove our very last theorem.